everyone. My name is Marianne. I'm a former physicist turned data scientist. And this is Jorn, also former physicist, and now he works in finance. But I first want to know something about you. How many people came here to hear about quantum computing?
Oh, that's good.
That's actually a lot. How many came here to hear about cats?
Ah, even better, even better.
One of you is going to be disappointed. I won't say which one, but you'll find out soon enough.
Or maybe both.
Or maybe both. Let's hope not. So the reason why we're talking about this is back when I was still in grad school, there was some talk about quantum computers and well, they used to say a lot of big things about quantum computing then already, but the criticism was always, okay, but what can you do? They would talk about Shor's algorithm and about factorizing prime numbers and how that would affect cryptography. And then if you ask them, all right, but what does that do? They could say, well, we can tell you that 15 is factorized by 5 and 3. And I would say, yeah, but so can I. You know, it's not very impressive. But really, why we're here is we have this conference, and there's all these talks that are about making you more productive and about writing better code, making fewer mistakes. But we're getting all too good at our job. You're all way too good. And all your code is way too error-free. It does what you want it to do. You test it continuously. You get great code reviews. So we also want to add some more excitement in your lives by teaching you something that'll make your code buggier and perform less well and add more surprise to everything that you do. So you're welcome. We're here to help. So what has changed since we first heard about quantum computers and that we learned the magic fact that 15 is 5 times 3? Well, this is quite timely because while we were preparing this talk, Google claimed to have reached quantum supremacy. So what quantum supremacy means basically is that they found that they can now do something with a quantum computer that you couldn't do with a classical computer, even a supercomputer. So the holidays are coming up, and I'm going to be going home, and I want to buy my mom something different. And I want to do something fun. So should I buy her a quantum computer? So the question is, let's say I want to fork over, I don't know how much it costs, but let's say I want to fork over that cash. What can I buy for my money? So I've just made a spec sheet. I thought, that's how you make decisions. What can you buy, if you buy a classical computer, and what can you get with a quantum computer? So, well, should I buy her a quantum computer, do you think?
Of course you should.
All right, well, sell it to me.
Well, okay, so on the left you have a standard Intel CPU, probably in the laptop you're presenting it. It does exactly what you want, it works, but we all know it's no fun. Take this guy on the right, the IBM Q. First of all, it looks good, right? Way more intricate.
But they're only showing one tiny bit of it. I'm sure it's huge and ugly.
Oh, yeah,
outside.
it's massive. You need some space. But I think the interesting bit is it has not 64-bit, but 14 qubits. So the qubit is going to be the quantum bit. It's going to be the interesting bit. So I think you should try it out.
Okay. But the price is a little bit steep, I noticed in the
Well, it's something new, right? It's always when you buy something new, it comes with a high price.
I mean, Mom, I love you, but $5 million. Okay, but I see something with a gate error. I see E-21, E-3. I don't know. It seems a little bit error prone to me.
Let's talk about that later.
Oh, okay. Okay, I'll start saving. So what are these qubits that he was trying to sell me on? Well, if you look at a classical computer, you all know they're bits, 0 or 1. But a qubit can be a little bit of both. So what does that mean? We're depicting a qubit over there as a sphere. So the state of a qubit is some value on that sphere. And rather than 0 or 1, which are two discrete values, the sphere is actually continuous. So it can take you could say, an infinite number of values. So the trick here, of course, is you don't know what value it is until you measure it. And in quantum mechanics, measuring is actually interacting with the system and causing its state to change. So when you measure it, its outcome will be either 0 or 1. So you're still, again, have only two states. But if you do it many, many times, then depending on where it is on that sphere, the outcome, the distribution of the outcomes will tell you something about what the original state was. Not everything, but it'll tell you something. And that's also kind of the richness that these qubits bring. So let's talk a little bit more about what you can do with these weird quantum states on that sphere. Or first, actually, let's talk a bit about quantum states, the quantum state itself. So there was a famous physicist, Schrodinger, who had an even more famous cat. So maybe the cat lovers here are actually happy after all. Well, until you see that vial of poison, maybe you'll be a little bit less happy. I'm sorry. It might turn out fine. So you have a cat in a box. You cannot see it. So that's important for quantum mechanics. You want to not observe the state, because observing is interacting and kind of destroying the quantum nature of that state. So you have a cat, and it's in this closed box that you cannot observe some process that can either not or not, that can happen or not, some quantum mechanical process, say, could occur, and if it occurs, some lever will drop, and the vial of poison will be opened, and the cat will be dead. I'm sorry. Or it doesn't happen, and then the cat is alive. So these are our two. Oh, sorry. So these are our two cases, right? Cat stays alive, cat doesn't stay alive. But the funny thing about an interpretation of quantum mechanics is that until you check, so once you check, it's either dead or alive. I mean, we know that. I mean, if we open that box, we don't expect it to be in some weird, we expect it to be either dead or alive. But until you check, it's both. And that's the crux of this superposition, this quantum state. So what can we do with these, how can we do something with these qubits? And especially what kind of things can we do that we cannot do with classical bits? So here you see one simple gate, a NOT gate, that acts on one qubit, and it just negates everything. It just inverts the state. It does kind of what you would expect, right? So if you have a state pointing that way, it points the other way. And if you look at the probability measurements, they are also inverted. And there's other states, like, for example, this rotation. It's a rotation around the axis of measurement, and you might expect something to change if you change the arrow, but in this case, you don't see anything. So if you just do this and then directly observe it, there won't be a difference. So the difference happens only if you do multiple qubit gates. So an example of a multi-qubit gate is making entanglement. So entanglement is a really weird quantum phenomena where two qubits kind of know something about each other, even though you can't explain how. So classical correlation typically involves some kind of information being passed in some way, but quantum correlation or entanglement is something that can exist even if there's no causal connection between the two. So you can have one qubit here, another at the other end of the universe, and they're entangled. If you measure one, you know what the other is, even though the measurement of the one could still be random. So here you see basically two qubits. You measure them individually. You measure one, it's 0 or 1. You measure the other, it's 0 or 1. And basically all the combinations, 0, 0, 0, 1, etc., all of them are, let's say, equally likely. This is just one possible state. They're all equally likely, no information about them whatsoever. But you see the bottom one, this is how we depict an entangling gate. So what you see is, I've painted the arrows orange, but other than that, the state hasn't changed of the individual ones. If I measure the top one, it's still 0 or 1 with the same probabilities. If I measure the bottom one without having measured the top one, if I just measure the bottom one first, it's 0 or 1. Both can happen. But then if I measure one and then measure the other, actually they are correlated. So in this case, I've correlated them in a way that if one is 0, the other is 0. If one is 1, then the other is 1. Doesn't matter what order you do it in. So that's entanglement. So now Jorn is going to tell you about a real-life example that you could use this in. It won't work great. I'm just...
Hey, hold on, no spoilers, please.
Oh. So, Jorn, take it away.
All right. Okay, thanks for putting up with the physics. And now we're going to get the example. So we have the super hard problem, right? So we have 8 dots here. And you want to group them in 2 natural groups. So of course anyone can do this. Probably even the cat, if it's still alive, can do this. But in general, in data science, this is a problem we see often. We have lots of points, and then typically in higher dimensions. And it's actually an NP-hard problem. We have something like k-means, but it's only an approximate solution to the clustering problem. And what we want to show here, the 2 concepts Marianne just illustrated, superposition and entanglement, how we can exploit that to run it on an actual quantum computer and efficiently find good solutions. So let's see how that works. So let's go over it one more time. So the nice thing here, what I depicted is basically all possible cluster configurations. So if you have m points, say 8 in this case, then you have 256, and you load them all simultaneously in memory. So that's something you can't do on a classical computer. Well, okay, if it's 8, maybe you can, but say if it's 53 qubits, the one Google used, then you have about 10 to the 10 possible configurations, and no way you can load that in any supercomputer simultaneously. But on the Google one, you can do that. So that is already a nice feature about the quantum computer. But this alone will not help you a lot. So what we need is actually entanglement. So that is a way to add information to the system. So on the right, we see all qubits, and they're all in some state, but they're still independent. But then you can add something like all these lines that somehow denote entanglement, so they know about each other. And then the superposition should actually change and should go to a state that you're actually interested in. So, all right. Yeah, we talked about cats, we talked about physics, but I think this is a Python conference, and we haven't really talked about that. So last minute we thought, okay, well, we have to do something about it. So we hacked together a notebook. And the great thing is IBM, they have actual quantum computers that you can access on the cloud. And they have even some packages for that, which you can easily install. That's all demonstrated in this notebook. So basically what I'm going to walk you through is what I did is to run a clustering example on an actual quantum computer. I'm not going to run it live because I'm sure I will mess it up. So I will just go quickly through it. So this is basically it. So actually this graph, this is so-called the quantum circuit. I actually generated it also with the same notebook. So on the left, we create a superposition I just talked about. Then we have a few layers of entanglement. And then we do a measurement. And hopefully, we find a good cluster. So let's look one thing deeper. So I have all these purple boxes. They're actually a sequence of smaller quantum gates. So some of them Marianne already touched upon. And this is what I needed to create some sort of entanglement. It doesn't matter if you don't get all the details. So here on the left, you see actually the code I use. So it's pretty straightforward. Pretty much every line is a box there. So that adds another circuit. So instead of, say, an AND gate or whatever, it's this quantum NOT gate Marianne touched upon. And she showed another gate to create entanglement. And I combined all these here. And there is some parameters. And I can use these parameters to tune how much entanglement I want, or what type of entanglement. So on the left here, we see if you tune it that way, then if you measure one particle and it's 0, then the other one will be 0. If we go all the way on the other side, if I measure 0 and 1, then it will guarantee to get a 1 in the other one. So they will have opposite spins. And this is very useful if you want to implement this for clustering. So let's go over the circuit. So again, we have added a few lines of code, and that basically gives you this first block. And this just creates you the superposition, so it basically tells you load all possible configurations at once in memory. All right, so let's do actually a measurement at this point. Let's see what we get. So what we have here is, so this is energy, we're still physicists, but basically all you need to remember on the left is the best cluster, and then the right is the worst cluster. And then we have these probabilities. So if you do one measurement, what is the probability that you get, say, the best cluster? And it's below 1%. And actually, all of them are equally likely. So at this point, it's just a quantum lottery. We haven't gained anything. You can just flip a few coins and try the configuration out and see, oh, this is my cluster. And why? Well, if this whole graph is empty, that means there's no entanglement yet. We have not supplied any information yet. So it's actually not really surprising it doesn't work yet. So now the next step, all these pink boxes, we basically take the code is above, but again, it's straightforward. So if we go back to our cluster, one thing we can do on a classical computer, I can compute the pairwise distances. That is straightforward. That's actually only a quadratic problem, so you don't need a fancy computer for that. And if the two dots are close together, I want to entangle them that they end up in the same state. So I don't know yet if they belong to cluster 1 or 2, but if I say this one, if I measure that this one is, say, in the first cluster, then it's very likely that this one should also be in the first cluster. But it could be that both of them end up in the second. So we have not made any cluster assignment yet, but only pairwise relations. So, okay, we have added that information out to the system, and let's see what we get. All right, this is starting to look better. You see that now some states are more likely, so the best one, now we have 4%, and some states we won't measure at all. And you can see that, so we have now some entanglement in the system, but there is still, at some places, there's no entanglement where we have not fully exploited all the information yet. So let's do just another layer. And so now we take different pairs. Because before that, we could basically split the system in exactly two sets, which don't know about yet. So by adding these extra pairs, now everyone knows about each other. So let's see what we get. All right, so now the best cluster is 12% or so. That's not bad, I would say. And the worst cluster is really small. And if you see, the entanglement is, it's decent. It's spread out over the system. So again, I want to emphasize that this is all, because we have only a few particles, is simulation, right? So normally you can't really compute all these things if you run this on a quantum computer. So let's do this actually on an actual quantum computer. So I have already done that. So all you need to do is you need to go to the IBM website, you create some account, you go online, and then on the right you see some devices that are online and what the queue is. So you pick one, I picked the top one in this case, and then basically you load up your circuit we had defined earlier, and then you run it, and then we can see what comes out. So let's see, so this is the actual result. So the blue ones, that is the simulation, and then orange is the experiment. So the correlation between these two is 53. It's okay-ish, but something that doesn't look good at all. If I look at the best state, that's only 2%. Come on. We had these 8 particles in this quantum computer, this $5 million thing that the best it does is assigns a 2% probability to this state. This is not really that impressive, I would say. And I actually, when I was playing around with this, I initially had the better solution. But then I thought, let me clean up the code a bit and made the small tweaks. I thought, this is better. But then actually the result went down. And I spent the whole weekend trying to figure out what changed. And then I was digging a little bit deeper. And since we run this on the actual hardware, let's see what the hardware does. So on the IBM website, you can actually basically get the configuration of the quantum computer. And here you see these 14 qubits, and you have these colors, and these colors tell you what the gate error is. So what Marianne was worried about at the beginning, like, oh yeah, this gate error seems a bit high. Yeah, it is actually a bit high. And it depends on the actual, say, number 4. That this is actually quite a poor qubit, but then the others are a bit better. So what happened when I changed my code, my configuration changed over this, and then I got the alignment was less good. So I have not done any optimization here. So this is actually a real problem in quantum computers yet. So that's why we haven't got amazing results yet, that we need to tackle this somehow. And that is both a challenge for physicists. They need to basically improve the hardware, but it's also a challenge for computer scientists, because you can, for instance, add a few extra qubits to do some error correction. And I have not done any of the quantum correction. I just did the plain vanilla one. I thought, okay, intuitively works fine. But yeah, and then in practice, yeah, slightly, some more work to be done here.
Are you telling me I should get my mom a book?
A book?
A book instead of this?
Yeah, maybe for now. Maybe hold on for now. Yeah, hold off on the quantum computer. Yeah. Okay. So this is only one example, but what I want to stress here, I chose the clustering. I don't want that you walk out now and then you think, oh, I'm always using k-means of scikit-learn, and now this dude is telling me I need to use a quantum computer. No, that is not the message. And the only reason I chose actually clustering, because it's nice to illustrate the concept of superposition and entanglement on a quantum computer. There are actually other interesting problems. So let's look at a few of those. So the first one, that's what Marianne mentioned. So that's Shor's algorithm, prime factorization. The record is now maybe 21. So there's improvement, right? Not 3 times 5, but 3 times 7. But the second one is actually more interesting. So normally if you want to, say you have a phone book and you want to look up someone's, say you get the phone number and you want to know who that person is. This is an old school paper phone book. When I was in undergrad, we still had those. Then you need to basically do a linear search. So that's an n problem. But you can actually implement quantum algorithms where it's square root of n. So that is a big speed up. And the other thing is, I showed the clustering, but there are actually a lot of business problems that require solutions, but finding the exact solution is MP hard. But we still need a good solution. So the traveling salesman problem is a good example for that, where, say, some salesman needs to go to different cities and they want to find the optimal route. And then you ask the mathematician, so what is the best route? And the mathematician says, I don't know. But still, the salesman needs to go on the road and sell his stuff. So you want to quickly find good solutions. So that is in the same spirit as we did the clustering. You could tackle something like traveling salesman. And more general, you can actually do many discrete optimization problems. Actually, Marianne is working in a farm and she's thinking about actually where she needs to do a lot of optimization, actually getting the quantum computer, right? So you're going to buy it for yourself. All right. Thank you. And I think I need to click one more slide. Yes. The cat is alive.
We measure.
Any questions?
Good news, we have a lot of time, so feel free. Which brave cat wants to meow?
Oh,
1 minute.
I see a question over here.
Okay. We got time for one cool cat. There we go.
Oh.
I was looking at MIT's course offering quantum computing. Have you guys looked at that? And also, can you really use Python libraries now for quantum computing?
I'm not sure which exact MIT course. So there's another course on EDX, that is quantum machine learning, that heavily relies on QAS kit of IBM. So our talk is a bit inspired by that course, actually.
And I think Google is offering on the topic. You know what they're saying? They're saying they got supremacy on that. That's Google, so.
I don't think, so sorry, you're asking if Google open sourced their?
Yeah, is there any courses on that? Because Google is now claiming supremacy on quantum computing. If you heard the news, you haven't?
Oh, so to the Google, yeah, so that is the slide we started off with.
Okay.
And so basically what they showed, so they used 53 qubits, and they solved the problem which you can't solve on a classical computer. But what they solved is they basically, you have this problem in computer science where you have a random number generator, and you want to test how truly random that is. So it's actually, from a computer science point of view, an interesting problem, but it actually hasn't any applications as far as I know. So they solved that problem, but no business problems yet. So yeah, they have the breakthrough, congrats to them, but we still need to wait for the first actual problem that we can solve without a classical computer.
Thank you. That's a wrap.